Everything you learned in high school chemistry about, what an atom actually looks like.
Oh, right, those blurry, swirling, continuous clouds.
Those fuzzy little clouds of electrons orbiting a central nucleus. I mean, we all had that iconic image in our textbooks.
Right.
Well, I want you to take that image and just throw it completely away.
Which is saying something because it's arguably like the most recognizable image in modern science. I mean, the foundational idea of standard quantum mechanics is that the world at the smallest scale is inherently, well, it's a smear of probability.
Exactly, a smear.
Space is a smooth continuum, and particles exist in the state of continuous, wavy motion.
But today, we are looking at two incredibly fascinating papers on something called Gibsonian physics, and they argue the exact opposite.
The literal exact opposite, yeah.
So the mission for our deep dive today is to explore this radically different model of the universe, one where atomic orbitals are not blurry clouds at all.
Right, they aren't clouds.
Instead, they are highly structured, geometric-like, discrete traffic patterns on a three-dimensional grid.
We are talking about an absolute paradigm shift here. The sources we're unpacking today move us away from a reality defined by those continuous wave functions,
Yeah.
and they push us toward a reality defined by strict localized counting.
Think about it like looking really, really closely at a video game screen. So when you zoom out, a character running across the screen looks like smooth, flowing motion.
Wait, this is continuous.
But when you zoom all the way in, you see it's actually made of discrete pixels. In this Gibsonian framework, reality itself is basically pixelated.
There is no smooth motion at all.
None. There are only strict turn-based rules. And in this deep dive, we're going to explore how this pixelated grid and a concept called token exchange builds the very first two atoms of the universe, hydrogen and helium, from the absolute ground up.
But I mean, an empty grid doesn't really do much on its own, though. Before we can build an atom, we have to understand the physical substrate itself. We need to look at the hardware of the universe, which replaces the empty, smooth continuum of standard physics with an actual physical lattice.
It's the fundamental board game that this atom is being played on.
Yes.
And the papers describe this lattice as being made of nodes called S-units.
Yes, S-unit.
And the defining geometric feature of this space is that every single S-unit has exactly 4 neighbors.
Right, it's a tetrahedral substrate.
Okay.
So you have 4 points connecting at every intersection. This is the stage where all physical phenomena occur. But just having a stage like an infinite network of nodes isn't enough.
Right, you need things to actually happen.
Exactly. You need a mechanism for time and motion to occur. In the classical view, time just flows forward continuously, like a river. But here, time and motion operate on a currency.
A literal currency.
Yeah.
I love this part. The papers call them tokens or T-particles.
Yeah, time is basically a transactional exchange. The lattice operates on this foundational rule called the full complement rule.
Okay, unpack that rule for us.
So an S-unit, one of those microscopic nodes on the grid, can only tick forward in time, meaning it can only advance its state when it receives a full complement of tokens from its 4 neighbors.
Wait, I want to make sure we are visualizing this correctly because it sounds exactly like a cooperative turn-based board game.
It really does.
Imagine you are playing a game with 4 of your friends. You have a game piece on the board, but you can't just slide your piece across the table whenever you feel like it.
Right, you're locked in.
You literally have to wait until you collect an action point, a token, from all 4 of the squares bordering yours. Only when your token budget is fully balanced are you legally allowed to make a move to the next square.
Yeah, and take that board game idea a step further. Standard quantum physics relies on infinitely continuous, incredibly complex differential equations to describe how a particle moves, right? Or how a field propagates over time.
Oh, yeah. Tons of calculus.
Exactly. It assumes you can slice space and time infinitely thin, but the Gibsonian framework it throws calculus out the window.
Completely out the window.
It replaces those differential equations with simple, token-weighted, discrete arithmetic.
Meaning we stop trying to calculate a continuum limit, and we literally just count the tokens moving between the nodes.
Yes, it's an exact accounting system for the universe.
That is so wild.
We just look at the deterministic difference equations. It is a strictly countable reality.
So, okay, we have our tetrahedral board, and we have our token currency, but an empty board passing tokens back and forth is just a blank screen. We need a player.
Right.
If we don't have smooth motion, and everything is jumping from node to node, what exactly is an electron moving on this grid? I mean, it can't just be a tiny billiard ball.
No, in this model, particles are not physical objects in the traditional tangible sense. They are stable, localized disturbances.
Okay.
They are closures on the lattice. Specifically, the framework defines the electron as a twist-2 closure.
Okay, let's unpack twist-2 closure, because that sounds like some heavy jargon. What actually is a closure?
A closure is basically a pattern of token exchange that cycles back on itself. So it's a closed token loop. And the 2 in twist-2 just means it requires 2 winding phases to complete its loop.
2 phases.
Right. It has to wrap around the local tetrahedral geometry of the grid twice before it gets back to its starting configuration and, closes the loop.
But moving in these tight winding loops on a grid where you only have 4 options per intersection, that has to cause some kind of bottleneck, doesn't it? Like you're constantly forcing this pattern to turn sharp corners.
Oh, it creates a massive geometric bottleneck. The framework calls this the inversion stall burden.
Inversion stall burden.
Okay. When this closed token loop is navigating the 3D lattice, making those constant tight turns to maintain its twisty-2 pattern, it creates a geometric lag.
A lag.
Yeah, it takes longer to acquire that full complement of tokens from its neighbors because of the complex routing required just to close the loop.
Wait, okay, hold on. If the grid requires exact counting to move forward, and this winding loop causes a lag in acquiring tokens, does that mean mass isn't a physical thing?
That is exactly what it means.
Are you saying an electron is basically playing a microscopic game of Snake on a 3D triangle grid?
Right.
And what we perceive as its mass is actually just the lag it experiences from constantly having to turn corners?
Yes. Mass is not some magical intrinsic property. It's not a heavy substance inside the particle. Mass is persistence burden.
Wow.
It is the geometric stall cost of maintaining that specific closed loop on a discrete grid. The resistance to acceleration we actually feel as mass is simply the lattice struggling to route the tokens fast enough to keep that specific complex pattern moving.
That completely flips how I was taught to think about gravity and mass. It's just
Lag. Just lag. And it explains why the electron takes the specific form that it does. The twisty-2 closure turns out to be the lowest stall, most stable charged loop possible on this specific tetrahedral lattice.
so it's the most efficient.
It is the path of least resistance for a closed loop. Any loop simpler wouldn't close properly, and any loop more complex would have a higher stall burden, meaning it would be heavier, more sluggish, and ultimately less stable.
Okay, so we have our player, this digital snake-like twist-2 electron. Let's look at how the very first atom in the universe forms. Let's drop this electron next to a single proton and build hydrogen.
Okay, so you start by placing a Z equals 1 nucleus, a single proton on the grid. This nucleus acts as a token source. It emits what the paper calls a radial Coulomb token field.
So it's throwing tokens out into the lattice in all directions. And since the electron desperately needs tokens to overcome its stall burden and keep moving, it gets pulled in.
Right, it feels the attraction.
So if the nucleus is throwing out tokens and the electron is starving for them, the electron just falls straight in, right? It just crashes into the center to collect all the currency.
You'd think so. But remember the absolute ironclad rule of the board.
Oh, the full complement rule.
Exactly. The electron loop is attracted to the inward tokens, yes.
Mm-hmm.
But to actually advance its state and survive without stalling out entirely, it must maintain a balanced token budget from all of its neighboring S units.
Not just the one facing the nucleus.
Right, all 4.
So if it gets too close to the center, the geometry gets too tight. It's getting plenty of tokens from the inside, but it's physically choking itself off from getting the required tokens from the outside S units.
The geometric inversion burden spikes. If it moves too far inward, it can't satisfy its full complement and the loop stalls. But if it moves too far outward, it doesn't get enough tokens from the nucleus to overcome its baseline mass lag.
So it's caught in a push-pull.
It is caught in a geometric push-pull, and the framework calculates the exact fixed point where the token attraction perfectly matches the centripetal motion requirement and the geometric stall cost.
The Goldilocks zone.
Exactly. And that stable fixed point happens to perfectly match the known Bohr radius.
The famous Anat. Oh, wow.
Yep.
For anyone listening who ever wondered why electrons sit at specific distances from the nucleus, this is a massive realization. The Bohr radius isn't some, arbitrary quantum magic boundary that an electron just decides to inhabit.
No, not at all.
It is simply the optimal traffic lane on the lattice, where the inner and outer token budget perfectly balances out.
It is the lowest stall twist-2 shell that the grid can physically sustain. And the lattice structure dictates something even more remarkable at that specific radius.
Which is?
Because the grid is discrete, The available speeds for the electron aren't continuous. At the Bohr radius, there is a natural ladder of exactly 137 possible subliminal velocity slots.
Velocity slots, meaning there are exactly 137 possible speeds below the speed of light that the electron can travel without breaking the token budget.
Yes.
You can't have a speed of like 136 and a half.
Exactly. You cannot have a fraction of a move on a discrete grid. There are 137 legal speeds, which, anyone who has studied physics will recognize as the inverse of the fine structure constant.
Oh my gosh, that is incredible.
Right. The fine structure constant isn't just a random number plugged into the equations to make the math work. It emerges directly from the grid capacity at that specific optimal radius. The geometry of the substrate actually dictates the quantum energy levels.
It takes something that always felt totally abstract and just grounds it in pure structural logic.
It really does.
Okay, so hydrogen is one car driving on the optimal track.
Yeah.
But let's escalate this. What happens when we add a second electron to make helium? How do two cars share the exact same track without causing a massive pileup?
So this is the exact problem where standard physics starts to rely heavily on mathematical approximations. Helium has a Z equals 2 nucleus. That means it has 2 protons, so it is throwing out twice as many tokens into the field.
Okay, twice the tokens.
And it has 2 of these twisty 2 electrons. Both of those electrons want to occupy that exact same lowest, most efficient radial track, the 1's shell.
And in standard physics, we use messy, continuous equations to calculate how the two electrons repel or screen each other so they don't try to occupy the exact same coordinate at the exact same time.
Which works as a predictive calculation tool, sure, but the Gibsonian framework argues it is conceptually backwards.
Backwards how?
Well, instead of starting with a continuous space and trying to approximate repulsion forces, Gibsonian physics solves the helium problem by literally counting the available traffic slots on the grid. They call this Tetra-Native counting.
Wait, what does Tetra-Native counting actually mean in plain English?
It means we look at the 4-way intersections of the lattice and we calculate the exact mathematical probability of a traffic jam.
A traffic jam.
Right. We are looking for the fraction of local paired shell microstates that are mutually burdening.
Okay, translating that for the listeners.
Yeah.
We're basically looking for the exact moments where both electrons try to use the same intersection at the same time, forcing them to stall out.
Yes, exactly.
So let's walk through the math on this because it builds on itself step by step. The source paper states that the base tetrahedral burden, just the fundamental cost of operating a loop on a 4-port grid, is a fraction of 3/8.
Right, 38. That is the base cost of existence on the lattice. But to figure out how 2 electrons survive in the same shell together, we have to apply 2 non-collision factors to that base cost.
Okay.
The first is the radial non-collision factor.
I want to visualize this using the train analogy we used earlier. We have an intersection. How do we count the radial choices?
Okay, visualize a 4-way intersection on the grid. The road behind you is the one anchoring you to the nucleus, pulling you inward.
Right.
Because that port is tied up just maintaining the inward radial connection, you only have exactly 3 choices for where to drive next. Those are your 3 outbound ports.
Okay, 3 outbound ports.
Now, combine that with the electron's wedge cycle rhythm. This is essentially the 3-step engine rhythm it takes to move forward through its twisty 2 phase. 3 available outbound ports, multiplied by the 3 steps of its rhythm, gives you 9 possible radial microstates at any given moment.
9 possible schedules for the trains to pass through the intersection.
Yeah.
And they have to avoid the single direct collision state where they hit head-on, right?
Exactly.
So out of the 9 possible radial schedules, 8 out of 9 states survive the intersection without a traffic jam. That gives us a surviving ratio of 8/9.
Perfect. The radial factor is 89, but the paper introduces the second factor, the explicit angular or spin ratio. This governs their tangential movement along the surface of the shell.
How does the angular factor work? Is it the same logic?
It follows the exact same local grammar, yeah. On the tangential surface of the shell, you again have 3 available ports, giving 3 local angular classes. But remember, the electron is a twist 2-2 closure. To share the space, the 2 paired electrons occupy what the paper calls opposite parity branches.
Meaning they are moving and mirroring opposite directions to avoid each other.
Yes, mirroring paths. Because they are on these mirroring opposite parity branches, it introduces 3 possible relative branch phase offsets. Think of them as 3 possible relative timetables for when they cross paths.
So let me get this straight. We have 3 available angular ports on the surface, multiplied by 3 possible relative timetables for crossing paths. That gives us another 9 possible microstates.
9 relative angular microstates. And once again, exactly one of those states is a maximal coincidence state, the exact moment their mirroring paths put them at the same port at the same time.
That total crash.
A total crash. So you exclude that one neutrally burdening state, and you are left with 8 out of 9 surviving states, another ratio of 8/9.
Okay, let's put the whole equation together.
Okay.
It is a rigid, mathematically pure timetable. The base burden of existing on the grid is 3/8.
Yep.
We multiply that by the radial non-collision factor, which is the 8 out of 9 surviving states, so 8/9. Then we multiply that by the angular non-collision factor, which is also 8 out of 9 surviving states, another 8/9.
So 38 multiplied by 89 multiplied by 89. The 3's and 9's cancel out beautifully in the cross multiplication, and it perfectly equals 8/27.
8/27. Wow. And that fraction isn't some, parameter tuned in a lab to fit experimental data.
Not at all.
It is pure combinatorial geometry derived straight from counting the traffic options on a 4-port intersection.
It is entirely derived from the structural logic of the tetrahedral grid, and the implications of that pure geometric fraction are staggering. It perfectly predicts the first ionization energy of helium.
Which is the real-world measured energy required to strip an electron away from a helium atom.
Yes, if you plug that purely geometric 827 screening factor into the standard energy equation for a Z equals 2 nucleus, you get exactly 24.55 electron volts.
Wait, really? It just matches reality perfectly?
It matches reality, and the source points out that this isn't an isolated coincidence. The paper runs sequence tests on heavier ions, too.
Like what?
If you apply that exact same 827 fraction up the sequence to a lithium atom missing 2 electrons, so Z equals 3, or beryllium, Z equals 4, it cascades accurately across all of them. The relative error is tiny, and it actually decreases as the nucleus gets heavier.
Meaning the underlying grid logic holds up under pressure. It's basically the fundamental traffic law for a paired shell.
It proves that the structure of the periodic table is a direct consequence of deterministic token-mediated interactions. It is a staircase of increasingly constrained traffic patterns trying to satisfy their full complement in a nuclear token basin. You literally do not need continuous wave functions to explain atomic structure.
A staircase of traffic patterns trying to hit their token budget. That is such a vivid structural way to think about chemistry. We've walked through a massive fundamental paradigm shift today. We have completely moved away from viewing the atomic world as an unpredictable, fuzzy probability cloud.
We really have. We have replaced the smear of probabilities with a deeply logical, computable reality built entirely on token exchange and rigid lattice traffic rules.
So hydrogen isn't a cloud. It's the optimal twist-2 snake, finding the perfect geometric token balance at the Bohr radius.
Right.
And helium isn't 2 clouds repelling each other with mysterious forces. It's 2 tracks perfectly coordinating their 9-slot radial and angular schedules to avoid that one crash state, yielding that beautiful 8/27th fraction. It's digital. It's countable.
And as the author of the paper's notes, these aren't just decorative examples or thought experiments. They are the mathematical proof of concept. The exact same discrete mechanism that governs relativity and field propagation in this model can carry the entire burden of chemistry.
Which leaves us with a truly mind-expanding question.
Hmm.
I want you to sit with this for a second as you go about the rest of your day.
It's a big one.
If hydrogen and helium, the absolute basic building blocks of the entire universe, are just the first 2 perfectly computable traffic patterns on this tetrahedral grid, what does this imply about the immense complexity of the chemistry happening inside your own body right now?
The implications for human biology are profound.
Are your cells, your DNA, your neural pathways, and life itself simply a vastly scaled up, perfectly choreographed exchange of tokens? Millions of little twist-2 closures, navigating a 4-port grid, just trying to get their full complement so they can take their next turn on the board.
It's incredible to think about.
The next time you look at a digital screen, I want you to zoom all the way into those individual, rigid, discrete pixels in your mind. Because according to Gibsonian physics, you aren't just looking at a screen. You might be looking at the true, unblurred blueprint of reality itself.